Okay, anyways, hopefully Nathan joins soon. What did I want to do? Right, we need to pull up the Remco post. Did you understand the notation that Nathan sent? Okay.
He sent like half a screenshot of his saying that I don't know. I don't think this works. Also, I don't even think you sent it to me.
I did on Messenger.
On Messenger. I have seen this.
Okay, so let me write what Nathan sent on the board.
Rip geometry.xyz down.
Yeah, geometry dead.
They're actually just done.
They're done. Quit.
They like took down the page too.
Yeah.
What about all the blogs they had?
Oh, that's unfortunate. I mean, maybe it's on whatever Kobe's calling the new thing. This is what Nathan sent. Okay, it shows up decently.
Oh shit. Forecaster release transaction frames.
LFG. That's cool.
Damn, he just doxed his net worth.
Oh.
Not that much.
No, I think that's just the amount he has in Coinbase, dude. He must be worth way more than that.
Yeah, but still. It's kind of hilarious.
witness times A times the witness times B is the witness times C. Right, okay. Yeah, okay, that makes sense. And then there's potential malleability in the public input unless linear independence is met. Right. Common reference string.
Yay.
What's up?
Discord works again.
Nice. Okay, so the CRS. This is gonna be G2. So this is alpha. Wait, the special thing about the SRS that nobody knows alpha and beta?
Yeah.
But then people know tau.
No.
No one knows tau.
All of those are hidden.
Great, okay. Yeah, I feel like I wish Ringo had said that in the post.
Generate random values to alpha.
Yeah, but he didn't say throw them away. Right?
I think he says it later that these can't be known, and he also talks about how they're actually generated too.
Yeah, okay. Right. Why do we construct L again? Why do we construct L?
That's just the magic polynomial.
Then what is
Just,
it?
combines all the shits. I feel like Groth16 does not have good intuition on a lot of levels, like why these things exist. Just sort of like it works.
Oh, you're right, since we don't know alpha and beta.
Immunify is what Dynamo used.
Yeah, they sent me that today. Alpha G1. Z is the low degree polynomial. No, Z is 0 polynomial, right? Oh wait, this is G1.
Okay, my laptop's dying. Actually, from this.
Oh, I brought you the charger.
No,
Oh, from
it's
there.
not charging fast enough.
Oh.
I'm just gonna head upstairs.
Okay, I can get you an actual charger.
That's fine.
You don't want to do this?
No.
Sounds good.
I mean, it seems like you're gonna re-understand Groth16, and then like this equation is like there's like too many different pairings involved for it to like fit nicely into the witness encryption thing. Seems like roughly where this is gonna land, and I don't really see any way to get out of there.
Good at the fact that you have like 3 pairings going on.
Yeah, there's like 3 different pairings going on. Yeah, like you're like, cause in the other thing you're like verifying a product with some pairings, but like I don't really see any way to like make that work with this. Oh yeah, wait, the reason I got Discord is just to see Sora's message about why this doesn't work.
Can you send me a screenshot for that as well?
Yeah. I think verifying IOP-based CKP scheme in the witness encryption is difficult because we need to compute a hash function for fiat Shamir transform. One interesting paper is Witness Encryption functional commitment. In subsection 5.2, introduces functional commitment for Groth16 proofs. It supports the Groth16 verification. The decryptor needs to know some of the proof in advance so that the decryptor needs to commit the witness at the time of encryption.
Decryptor needs to greet the witness.
In the sense that if you don't have the witness, then you won't be able to calculate that fiat Shamir hash properly. Is what you mean?
Say that again?
Like, in the sense that because Groth16 is implicitly verifying that fiat Shamir is calculated correctly, if you like, there's no way to do that inside a witness encryption scheme without knowing the pre-image of that hash, basically. Is what he's trying to say.
I just sent this screenshot to you. I don't think so. Like, I think those 2 points are separate. Like, he's talking once about so okay, there's witness encryption for functional commitment.
Yeah.
Is one thing, but for that, the encryptor needs to know some of the proof of advance. So the decryptor needs to commit the witness at the time of encryption, and then you can like encrypt to that witness. But then at that point, it's not really useful.
Yeah.
And separately, he says IIP-based DKP scheme of the witness encryption is difficult because we need to compute a hash function for fiat Shamir transform.
Wait, where does Groth16 verify that fiat Shamir transform?
It's actually a good question. There's no fiat in this. I also wonder if reading the witness encryption paper for KCG
Would actually help.
Yeah.
Yeah.
That I'm actually down to like go through and understand.
Okay, yeah, me
That's,
too.
like, actually a concrete thing that we can do. Whereas
Okay.
it seems like we'll just be scratching at the wall, getting cuffed.
Sure.
Because I'm sure then that will give a bunch of intuition for how to like do something more advanced than the
Sure.
plus one.
Oh, their repo is open source now.
Was it out before?
Yeah. Maybe I just didn't look before. I don't know. 3 days ago, yeah, dude, this is new. But 3 weeks ago, they committed Laconic OT. 3 days ago, they got the README. Yeah, this has been open source for a month.
Oh, it's just this dude. So beautiful. The KZG commit, the implementation of KZG is so short.
Huh? Oh, yeah.
It's the best polynomial commitment. All these motherfucking Starks break down.
Okay, yeah, I'm down to go through this. I agree. I think we'll get more out of doing this.
Okay, then in that case, I'm actually gonna get my charger. I'm just gonna get my thick socks. The floor is so cold here. Outlet is outlet. This house is outlet. So it's alright.
Dude, I'm actually dumb. I don't understand how Groth16 is verifying Fiat Shamir.
Do they have one? On this Reddit, it seems like they don't.
So then I'm confused why sort of the IOP thing doesn't, like, why that
I
applies.
sent him FFlonk when I asked him that question.
Because FFlonk have a Fiat Shamir verification?
I think so. I mean, I know Plonk does, but FFlonk, like, what was this?
No, it's just some random paper I pulled up that doesn't have to do with anything.
Can I get that monitor?
Yeah, Loki, that would be hype.
Here. There's an outlet here. There we go. Do you want to plug it in?
Yeah. There's also an outlet there. It might be easier to do it from because yeah, here directly under the table. I don't think that'll reach, dude.
You sure?
Yeah,
It'll definitely reach.
There's an outlet literally right here. Why don't we do it here? Yeah. It's a 2-prong outlet. Oh, you lied. You wrote 2-prong or 3-prong?
2 prongs. Or not 3 prongs, 3 prongs.
Oh yeah, yeah. See it there.
Okay, pull it out.
Should I hook up my computer?
I also kind of want to actually go through ZK creds.
What's ZK creds?
That paper I sent that did passport shit in 2022.
I doubt we're gonna learn like a ton of new stuff now.
They do some interesting thing with like linking Groth16 proofs.
Just by like witness commitments?
I think something slightly fancier than that.
Okay, I mean if it's fancier then I'm curious.
It's just like it seems like they have some sort of solution to nullifiers. But okay, this is more interesting anyway.
Yeah, I agree.
Okay. I'm gonna erase this right so far.
Huh? Wait, why?
Why do we need this for the other thing? You just copied equations from there.
Yeah, but it's nice for me to have it just written out like this. I mean, why don't you just erase that half and then I'll take a picture of that half, we erase it and then we can use that half.
You're like, why? This takes up so much space too. This is literally just the CRS. You can just recite this.
Okay, fine. You can believe Nathan's thing or?
What is Nathan's? I thought Nathan's thing was broken. It's like fine, right?
I mean, the problem is Nathan sent it in text, so it's just really hard to read. I'd rather. Why don't you write below it for now, and if you need space to erase it?
What is this business? Like it's just broken. Like why do we need this?
So I understand why it's broken.
I'll just explain why it's broken. It's fine.
Yeah. Whatever. I guess we're doing a different thing now, anyways.
Yeah. So.
Wait, so the verifier needs to compute the fiat Shamir value by hashing the commitments that the prover sent, right? So then, why in the Groth16 verification smart contract is there no SHA-256 step? Or is there?
I'm not sure.
Oh, what's up?
What's up?
Hey, how's it going? I think like, alright. Yeah. Just curious, what have you guys done so far?
Yeah, sorry. So we were initially going to look at the original proposal you sent, but then I think I didn't understand what like a couple of things were, like what was GT exactly, what was like, what about the construction you sent it didn't work, and so on. And so we decided to switch to your writing down the BLS SWE algorithm right now, right? And then we were going to look at the new KZG witness encryption algorithm. See that paper that came out?
Yeah.
Yeah.
Okay.
Yeah, and then also they released some code for witness encryption on KZG like maybe like 3 weeks ago. So we're gonna go through, maybe use some of that to help us understand. And then I had like a bunch of like extremely stupid like 0 level questions on like Groth16 that I like realized I didn't fully understand. Like for instance, Groth16, okay, like here's like a very like dumb understanding question is like, it should be the case that Groth16 is computing a fiat Shamir transform on the verifier side, right? Like it's taking the commitments, it's hashing them, and it's using that somewhere. But then and then it's using that as like the random challenge that they sent to the prover, right? But then in the actual Groth16 verification solidity contracts, I don't see any SHA-256 being called. And so the question is like, where is that fiat Shamir verification happening in the Groth16 verification? Is that like baked into the Viki, or is that like yeah, for some reason I realized I didn't understand that fully. Do you have an answer to that question?
There's no fiat Shamir in the paper.
Yeah, there's no fiat Shamir in the Groth16 paper.
Oh, in the Groth16 paper,
or like in the implementation and the understanding, whatever. It's not in the Remco blog post. It's not in the Groth16 paper. It's not in like any like reasonable thing. So.
I assume that wait, in the blog post, I'm pretty sure R and S are probably just or wait.
Well, the thing is that also like this Medium post I'm reading right now says all practical implementations except Groth16 use fiat Shamir. So my question is like, how the fuck does Groth16 not use fiat Shamir? Where does that random challenge like tau come from then?
Well, tau comes from the powers of tau setup.
So there's no random challenge. It's just tau is like we, instead of using a fiat Shamir challenge, we just use this random tau, and that's the challenge point. Is that how Groth16 works?
Like my understanding of why fiat Shamir is used for like Planck, for example, is because there's like multiple rounds of back and forth, where you like verify different parts of the equation at different times. Like you first verify like that the different like ABC stuff checks, and then you then check the copy constraints and stuff.
Right.
And the reason fiat Shamir is used is so that it's basically non-interactive. But it seems like Groth16 is more or less like one round, or maybe like in this sort of like phase 2 setup, they basically like they basically like, this is where the interactivity goes. I don't know. I don't have great intuition for why it's not there.
Right.
Or yeah, I don't think the prover needs any verifier randomness in Groth16. Like you're just checking on tau.
Right, so then, wait, so why do we not need a fiat Shamir? Because the random challenge we use is tau.
Wait, like to be clear, like the random challenge used in fiat Shamir is not like, I think what we're plugging into the polynomial. Like that's always like tau for a lot of these different things.
Yeah. But then in Planck you use fiat Shamir because you have like non-tau challenges at random middle steps.
I think there's like RLCs. Like you do RLCs.
Ah, right. You need to do the RLC. Right. Okay.
Of different polynomials, and that's
right. So you need the randomness for that. Right. I see. Okay. Versus here you just have tau is the only query you ever make to a polynomial.
There's like some RLC happening with this like beta and alpha stuff, but that basically happens in this phase 2 setup. So yeah.
Oh yeah, also this is on stream, in case you care, Nathan. 0 people watch the stream, so it's fine.
Alright, sure. Oh yeah, by the way, GT is just the generator in the target group.
Wait, sorry. There's G1, G2, and the last
GT.
G. Oh, the last G is GT, right?
Yeah, that's just a
Yeah.
generator.
Right. The generator in the third group.
It's just never like mentioned explicitly, but it's.
Wait, how is it not mentioned explicitly in the Remco post? And then what is it?
I mean, it's just. I mean, you can compute it from G1 and G2, so it's like it's not explicitly like.
Wait, is it G1? What is GT exactly? Is it G1 times G2, or is it a more complex thing?
It's just pairing of G1, comma.
Yeah, it's just
Oh,
each
right.
G2.
Right. Okay.
Yeah. Wait. So I guess Nathan, do you want to walk through the scheme you had, and also tell us where it broke, or like just some of the intuition behind it?
Yeah, or I guess like I can talk about. Or you guys know like the BLS, how the BLS thing works, right? So basically, I was trying to like imitate that. And I don't know if there's a good way. How do I connect my like iPad?
Yeah.
You can just join the Zoom.
Yeah, exactly. Just screen share your iPad on the Zoom.
Like if you have the Zoom app on your iPad, it should work.
I can share it with AirPlay.
Oh, and then you mentioned there were a bunch of typos in the Remco post. What exactly are those?
Low key. I didn't really look carefully, but I think it's mainly just like switching M and N.
Switching M and N. Okay.
In a bunch of places, yeah. Wait.
Where's M and N? Oh, I see.
It's usually the number of things in a.
Yeah,
so,
that got me kind of confused.
Right, so M is the power of 2 higher than the number of constraints, and N is the actual number of constraints.
Other way around, I think.
Oh wait, N is the witness size.
Yeah, that's correct. Yeah.
And M is the number of constraints.
Right, because the number of constraints is the highest power of 2 above the witness size.
Wait, it says. Oh, but you saying he switches it up a bunch of times? I see. Okay.
Well, but they should effectively be equivalent because you could just add a bunch of 0 constraints to N and then get M, right?
Sorry?
Like you just add a bunch of 0 constraints to N and then just get M and then use M everywhere, right? Which is what I'm under the impression that he's doing.
Oh, I guess he could. Or I guess because M is always just like, or yeah, I mean you could. I didn't know. I didn't think that was what I was doing.
Or it's just like M and N can be effectively equivalent, right?
Sure. Yeah.
Wait,
but
no.
like normally, like this, like M will be like super linear in N, right? So like you don't actually want that.
M will be super linear in N.
Like you'll have a lot more constraints, right?
Wait, no, M will be at most twice N, right? Because M is the power of 2 right above N.
M is the power of 2 right above N.
Right.
Wait, M and N should be unrelated.
Yeah, I think M is the upper bound for the number of constraints. Like, if, for example, in like Snark.js, this is like 2 to the 26 is like M, basically.
Oh, the highest possible number of constraints.
Yeah.
No. I'm pretty sure it's not 2 to 26. I'm pretty sure it's just like. Wait. How did you get that?
Wait, M is a power of 2.
Yeah. But then.
And
why
it
can't we
should
just
like
define,
upper bound the number of constraints.
Like, why can't we just define M as the power of 2 after N, and then you discard all the higher level trusted setups, and then just use that as our M and our N?
I think that's fine. It's just M is just defined as the upper bound.
Sure.
And you can use as much of it as you need.
Sure. Like, I think when he says upper bound M for number of constraints, he's not referring to like upper bound in all ZK proof systems. He's just referring here, like this is the like power of 2 that would upper bound the number of constraints.
I don't think it matters.
Yeah, I also don't think it matters that much. I think that's like a fine typo. But I can see I would make it like a little more difficult to understand.
Yeah, it does seem like he mixes this up a decent amount.
Like in the witness. Yeah, I see.
It's fine. This is parsable.
Yeah.
Okay, so nice, iPad's here.
Great. Your brightness is a little. Oh no, my brightness is low. Never mind. Okay, you're good.
Okay, so basically, Groth16 is checking the. Oh wait, let me use this shit. Where's the pencil?
On the side.
What the hell?
On the left.
I can just move the screen.
Like under the little arrow on the left, with the blue arrow.
This is a blue arrow. No.
Like look on the left side. There's like a tool
Oh, no,
select.
no,
Oh, that's
ours.
us. Oh, LFG. Wait, so if you draw now, does it draw, or is this an us specific thing?
I just moves the screen or my pencils. Oh, I can like see what you're drawing.
Yeah.
Yeah.
Just a horrible experience with a trackpad. I could connect my iPad too.
Alright,
We can also just let you draw, and we can just use text.
Okay, for sure.
I've never used this Zoom whiteboard thing before. That's crazy.
Yeah, so this is new, but yeah.
It is cool.
Wait. Maybe it's because like I'm not the owner, so I can't.
Oh, can I
Or I'm not
make-
like the Zoom.
Yeah, let me make you a
like-
co-host. Make co-host. Okay, how about now?
It works. That's so weird. Wait, I don't know. Can I not like? Let me try something else.
You can also just screen share Notes app if you want.
Yeah.
Yeah.
It's probably easiest at this point.
yeah. Okay. So. Groth16 is checking that something like this holds. But you guys can see it, right?
Yeah, we can see it.
Okay. And basically, this is like public, and we want the person to like provide A, B, and C.
Yep.
So, in like the BLS scheme, basically like the public value was your V key, which is like G to the X. And so what we did was we raised V key to like some random power R. And then we gave them G to the R so that they could like move this X, or like end up pairing like E of G to the VK, which is E of G to the, or G and G to the XR. We can like move this X over, or wait, no, we
Or
can
on the
move
left
this.
side, there's an R exponent, right?
Oh yeah, sorry. So we could move the R over,
Right.
and wait, how does this work?
And then because they don't know
And-
R, the only way they can calculate this pairing is by knowing G to the X, which means they have to know X. Or wait, something's wrong.
It's like so you compute sorry.
You can just refer to this. I think it's like
Oh, you put the VLSC up here. Oh, great.
it's very clear.
Wait, how did this shit work again? I just forgot. You're
Yeah,
moving
that's
this.
relatable.
You're moving some exponent over, basically.
Wait, you can look at my whiteboard, like the physical whiteboard here, and see it as well.
It's very small on the whiteboard though.
I can't really see it.
I can get my iPad potentially. Okay, so roughly what's going on is like your ciphertext includes like this G2 point to some random thing R, and then you take like 1/2 of the like signature verification equation, which is like the pairing of like
Oh, right. It's wait, sorry. Go ahead.
You're good. Okay, wait. Let's just write this down first. So like just for normal BLS signature verification, you have a sigma, which is essentially like hash of your message T to the power of X, where X is your secret key.
Yeah.
H is just hash to curve, to the G1 curve, and then the verification you're doing here is like pairing of sigma comma G2 equals pairing of h of t comma vk. So this is just BLS signatures. Like
Sorry,
this is
G2, not
sigma
V2, right?
VK, the verification key.
Yeah.
Verification key here being like G2 to the X, which is like your public key. Okay, and then so for BLS signature witness encryption, the ciphertext here is, it's like a pair of elements. So the first element is G2 to the R, or G2 specifically. And then a pairing of, it's like basically the right-hand side of the verification equation.
Wait, isn't it like this?
It's H of T, not G1.
Or it doesn't really matter, right? It's just like a public value.
Well, specifically, like this is like the hidden value that you're encrypting to, basically, is like the H of T. Like H of T in this case is like hidden. You're basically encrypting to someone, or no, sorry, H of
No,
T.
but
is
H of T is a
public.
value
Wait,
on the G1
your
code that you're
T is
effectively using as a
public.
generator. Like for you, G1 equals H of T.
Yeah.
Yeah.
Like it shouldn't matter, right?
Yeah. Times. Well, I guess like, yeah, it should be fine.
Because everybody knows
Or it's
G1.
basically like this.
Well, so then also, you multiply the like second component by like GT to the M power. This is
Oh
like
yeah.
the bit you're encrypting
Or
to.
you can also just like hash this and like XOR with the message. Basically, you're just extracting a message here.
Yeah, that works too.
But you want to like compute like this guy.
Yep.
And so like
Wait, what is message T? Wait, sorry. I thought message was T. What's M?
So
Oh, M is your bit.
that's like the message.
Oh, that's the message.
or M is
Got it. Yeah.
or I think it helps to like not think of there as T. Or I think it helps to like not have T at all.
Yeah.
Or you can think of T as just like an empty string.
Yep. This makes sense to me.
And then so like
yeah, the actual verification
It's-
then becomes like you XOR this second element here.
Wait, sorry. How's hashing the pairing an operation?
This is you're just
Or-
like XORing the message into like some SHA-256 of this. Like this is just your secret information.
yeah. Or hash you can just think of or you're just like converting into a bit string.
Yeah. And then yeah, so then
Like I think you shouldn't even like care about this part. Like you should just think of trying to extract this value.
no, I think the XOR is good. Like it's good to keep that in there.
Or like the hash thing. But basically once you have this value, you win because you can just hash it yourself and then XOR it with the ciphertext to get the message.
Oh, so the point is we want to get that value, fine, and then it doesn't actually matter what we do.
Yeah.
Sure.
Yeah.
Yeah.
Slight,
You really just want this.
Yeah. Okay.
slight correction on the bottom here is like it's G2R. Like it's pairing of G1 comma G2 of R, like the first element in your ciphertext.
Oh, sorry, where? Which one?
So like this bottom pairing you have, it's eq of G1 comma G2 to the R.
Okay. Wait.
Like
Or no, I think what you say, like, it doesn't, like, what he's saying is that, oh, because you need the S value, I guess.
no, the S is up. The S is just becomes 1 in this case. Like we have because we just made H of T.
Oh, I see. So what he's writing is correct then, like, this is the thing you actually want to calculate, right? Like, that's exactly what you wrote on the top.
Oh, I see. You just expanded this top thing. I see. Okay.
Yeah,
Then on
exactly.
the right hand side of this is E of G1 comma.
No, G1 to the X, comma G to the R, right? Like, you basically move X here and R there.
You don't have G1 to the X.
So this is like G1 to the R, or sorry, G1 to the X, G2 to the R.
You do it G1 to the
And,
X,
like,
that's the point of this, right?
To compute this,
The V key
you
is
do, like, need-
G2 to the X. Wait, something is off here.
No, this is exactly what you wrote on
Wait.
the bottom line.
yeah. Or basically like you have this value because it's provided in the ciphertext. And here we're assuming that like it's like an asymmetric pairing. So like G1 is not G2. And then like to compute G1 to the X, you kind of have to know X, basically.
Okay, I see. So usually in BLS signature witness encryption, it's not just G1. It's like H of T here instead of G1, but this works fine as well. Like what you have in
Yeah.
BLS signature.
Yeah, we already
witness
defined G1 equals H of T.
Yeah. So we're fine here.
Yeah. Okay. I think this is yeah. So basically, like, I guess the main idea is that here, like the V key that power of X is in the Jinsu, and you want to like move it over, to like leave room for like this guy, which you can like provide.
Or I guess like instead of moving over, it's like this is the thing that you want to basically encrypt to, right? Is this G1 to the X? Like this is the information you're hoping the other person has, and only they have.
Yeah.
And so then you're encrypting to that information. Like in the case of BLS signature witness encryption, it's like they have a signature on some message, which is basically the message to the
like
power of
HG
X.
to the X, yeah.
So this G1 to the X is basically like your hidden information.
Right, so that's the BLS signature itself.
Yeah.
Right, and then you need
Yeah,
that
I think you
value.
can think of it that way.
Right, and you need that value to be able to calculate this value for arbitrary R. Right, okay, I see.
Well, yeah. Because the R is given to you as like the first element
Yeah,
of the
exactly.
ciphertext.
There's no way to calculate this pairing properly.
So yeah, I guess the thing I'm perplexed about is basically like it seems the hidden information here is like G1 elements. It's like sort of elements in this group, but then when you go to the Groth16 verification, it's like a bunch of shit in GT land, right?
Yeah.
Because C is super
So basically, like the analogy doesn't really work when you try to like do Groth16, because basically, like you have this like you have this public value on the right, which like anyone can calculate, but it doesn't have a secret value really baked into it anywhere. Like, you know, on that, like for a V key, like the V key is public, but it has like this secret like X baked into it, right?
Right.
And that like gives it some actual like substance. Whereas
Yeah.
Wait, sorry.
like the right hand side of this.
So you mean like the V key, like when someone defines a V key has substance baked into
Like
it.
the V key, like somebody knows this X basically.
Right.
Whereas for Groth16, or like the V key like has some power in that way, but for Groth16, like this value is just like completely public and anybody can compute it.
Right. There's no like public private key pair here. It's just like that is the public key.
Yeah, so that was kind of my intuition for is like why like trying something similar to like BLS is not really gonna work.
That makes sense to me. Yeah.
Basically, originally what I tried was like you like raise this to the power of like some randomness R, and then you like give like terms that look like G1 to the R, G1 to like the R tau and stuff like that, so that you can like basically compute this in another way from here, from like these guys.
Yeah.
But the problem is like because like these values are public, or this value is public, it doesn't have like this secret in it, then it doesn't actually matter that somebody has this proof. Like anybody can compute it. And like I feel like I came up with like a pretty good example of like why this like actually matters. Because like if you think about like so
the private thing here is like the L polynomial, right? Like you can only compute the L polynomial if you actually have an A, B, and C that like satisfy this pairing, right? So it is exactly. So this L is basically your like.
No, this L bar is public.
Yeah.
It's completely public.
This is like the part
because
of
it only
the L.
depends on public inputs.
Right, exactly. There's like a part of the L that's like public. Also, the L is not the private part. It's like the fact that you can make a proof that makes this equation work is the private part, or like is the
So like for reference, L bar is
I see. Because in BLS you're proving that like you like eventually that gets proved is knowledge of secret key or something. But here in Groth16, it's like the eventual thing you're trying to prove is like, oh, I know two values such that when you calculate this pairing, the thing checks out, and then you get like the output of Groth16 is like a 0, 1. Like, oh, okay, like you knew these two like inputs of you knew some inputs of the pairing that would allow it to check out. Versus in BLS, if you pass, it's like, oh, you must have had like the ability to like take something to the exponent of a private key. Is that like the right intuition?
Or like I'm not actually sure because like when like if you try to do a formal security proof, like I'm not sure like if the thing you want to say is I claim or like I'm proving that I know like ABC such that this like pairing equation holds, or if you want to prove I know like private witnesses W like whatever such that this equation holds. I'm pretty sure you can just relax it to Groth16 because of like knowledge soundness or whatever. But I think it's a lot more like subtle than like you might think. But
Right.
but basically I claim like the problem with like having just this public value is you can consider like this like pretty similar or pretty easy problem, or not easy, a pretty simple problem where like I you have a CRS which is like powers of tau or whatever, or okay. And then basically I'm gonna encrypt to like something similar that looks like this. Key. So what I'm saying here is that I claim to know polynomials A and B such that like A times B is equal to V key, which is like G to the X or whatever.
Yep.
So like this is like kind of similar to like Groth16, right? It's just that like you have this V key on the right now. And I'm pretty sure you can do this very simply. I haven't actually
Wait, but the problem here is like
proved any security.
this V key now lives in
Okay.
like GT land, and you can't do products in the exponent.
Oh, okay, sure.
in GT
I can
land.
do like this. Okay.
Sure. Nice. Yeah. That works.
And so what I'm gonna do is I'm just gonna raise everything, or I'm gonna sample R and S from like some field, and then I'm just gonna compute like something very similar. This. And similar to how I provided like G to the R here, I'm gonna provide additionally like G to the R, G to the R tau, and so on, as well as G to the S, G to the S tau, and so on.
Mm-hmm.
And now, like, if I know A and B, I can compute this value, right? Because I can compute like A of R tau, and I can compute B of R tau, and I can pair them to get this guy.
Wait, B of
And
S
I'm
tau
like,
or B of
what?
R tau?
Oh, sorry, B of S tau.
Right, is that correct?
And I'm pretty sure that if you do not know A and B, then like there is no way for you to get this value, right? Because basically this is
Wait,
like
I don't think
G,
this equation
T.
works, right? Like, because like what's going on here is like you're
Wait, what?
multiplying. Wait, let's see. You're multiplying like the product of two polynomials.
Or sorry, not this. I should say R times A of tau.
Yeah, that works.
And
Right, sure, yeah.
X times, yeah, sorry. This, right?
I mean, it's the same thing because it's powers of tau anyways, right? So you're putting
No.
x in the exponent.
No, this is different because before you have like s squared tau squared, s cubed tau cubed, but now you just have.
Oh,
s.
fine. Yeah, you're right. Yeah. Okay.
And so I guess like security, like intuitively, my idea for security is that this is like GT to the XRS. And like if X, R, and S are all like uniformly random, then like there should be no way for you to compute this. This is like EDH assumption or something.
Yeah.
There should be like no way for you to compute this without knowing like something like G1 to the XR or something like that. So I've like sort of confident that this is like secure. But like the key idea here is that like we have like this secret that's kind of baked into the V key. That's kind of my intuition.
Sorry, secret baked into the V key. I don't understand what that means.
Like your V key is G to the X. And like, so like the way that we're actually computing this guy on the, right, is that we're kind of like, we have, the X, the R, you have, or how do I explain this? Like if like the term on the right was like, or okay, you can imagine something equivalent where there is no secret and you just have like, you have like A tau, B tau, equals like E of G, and like, I don't know if it's like a legit example, but like, basically, okay, you can get pretty trivial stuff with this. This is kind of stupid. Or I think like for here specifically, you kind of need this X to get like this security thing. Like this is like very good from a security perspective because this is just exactly what BDH says.
Sorry, BDH is what?
It says something like, given
Wait, what does BDH stand for?
bilinear Hellman or something.
Oh, right. Yeah. Okay, yeah, I know what you're talking about.
It's like, yeah. It's like if you have like G1 to the X, G1 to the R, G1 to the S, and so on, you can't compute like G2 to the X or F.
Right. Yeah, I know what you're saying.
Or you can't distinguish them or something like
yeah.
that.
It's like, yeah.
So we already kind of have some stuff that looks like this from like the phase 2 setup, right? Like in the phase 2 setup, the prover, or like whoever's involved in the phase 2 setup, basically sets up this beta and alpha that are random. Like, but the thing is like, this is so weird because in the BLS signature witness encryption case, there's like this like weird asymmetry where there's a dude who has a private key and he gives out signatures that sort of like feature that private key in some way. But through all of Groth16, like all the random values are sort of like generated in these setups that like no one really, no one is supposed to know any of these values if these things are generated correctly.
Yeah.
Well, but the idea here is that if you don't know the exact polynomials A and B, like if you don't have like an exact witness that satisfies them, then you can't do arbitrary computations on them, like toss an R on it. And so in a sense, this like A and B is your like the equivalent of the private thing that we're verifying in BLS, right? Like the fact that someone can perform this manipulation on it where you chuck an R here is only possible if you know each individual value for A and B.
Yeah, like here, like knowing A and B is pretty important, right? Because you're splitting R times S into like R times S, and you can like, if you only give this guy powers of R and you only give this guy powers of S,
then they need to know
they like kind of have
exactly.
to know this pairing to like compute it, right?
And so in this case, R and S are different than the R and S referred to in in Remco's books. Like this is new R, new S.
Yeah, like in practice, like R and S in the Groth16 proof can be set to like 1, right? Because you don't need zero knowledge.
Because you have what, zero knowledge?
You don't need zero knowledge. You can like hard code R and S.
Oh, I see. But if R and S
because
sure, but if R and S are unknown, then you get zero knowledge.
But you don't need zero knowledge.
But we want to do this in the zero knowledge setting, right? Or it's easy to add blinding after.
Because the decryptor is like, the decryptor has his proof. The decryptor never shares its proof, so he doesn't need like zero knowledge.
The decryptor never shares. Sorry, what is decryptor?
True. Yeah, you're encrypting to a valid proof, but like the encryptor never like gets the proof.
So there's prover and verifier. Who's encryptor?
Like in the way
there's no prover and verifier. There's an encryptor.
I see. In the witness encryption scheme, fine. Okay, yeah.
There's an encryptor encrypting to valid like proofs. But the person who does the decryption never gives up their proof, so the proof doesn't need to be ZK. That's a nice observation. Yeah, so we can actually get rid of R and S here.
The person doing the decrypting never gives out the proof.
Like they just have their proof.
Yeah, because once you encrypt the message, you don't you're done. Like you don't.
Because you don't actually need to do the verification, so you don't need this like blinding thing. Because you're not going to be sending those things on chain or anything. You're just doing the decryption locally. Okay, fine.
And like another thing that I kind of realized is that like the encryptor can know all of these secrets. Like they can know like tau, alpha, beta, like gamma, delta, or whatever, right? Because like it doesn't matter to them.
The encryptor can know tau because it doesn't matter to them. That feels wrong.
Because like the encryptor just has to sample these values and give the CRS to like the world. Nobody else knows like these secret values, but from the encryptor's point of view, like they can't do anything with these tau alpha beta, because like I mean they could generate
Oh,
like
fine.
fake
Because
proofs for their own
if they
chain.
had sent, fine, I see. Because if they had sent, like, if the decryptor had sent like A and B on chain or something, and the encryptor knew tau, they would be able to reverse engineer what the witness was. But because they're not sending A and B on chain, then we're like fine.
Yeah.
Or something like that.
Yeah.
Right.
Oh
okay,
yeah, I
fine.
didn't even think of that. They could reverse engineer. Could they? Wait, could you? Yeah, you probably could reverse engineer the witness.
Well, no, I think the problem with tau being revealed is that you can like fake it.
Hmm.
You can just find something where it works at that specific tau, even if you don't actually have a satisfying witness. The reason tau.
Yeah, but that doesn't matter if the encryptor knows tau, right? Because it like
Yeah,
the
because the
encryptor can
encryptor,
generate
sure,
all the
because we don't care if the
receive one.
encryptor actually has a satisfying witness or not. We only care if the decryptor does.
Yeah, exactly.
Yeah.
And so yeah, the encryptor,
So-
it's in the encryptor's best interest
Yeah, so-
to make it random.
Wait, so that's cool. So we don't even need to do like a trusted setup here.
Right.
Yeah, basically this kind of means that you can like extend your CRS to include a lot of like weird terms that you like didn't have in Groth16.
The problem is though, like this means that there's actually a significant communication complexity here for every single type of encryption. Is like, not only does the person need to post the like ciphertext here, or rather, yeah, the ciphertext. They also need to post like a potentially pretty long series of powers of tau.
Come on, but you need to post powers of tau anyways when you make a ZK proof. It's just here.
No, there's one powers of tau though. That's a
No,
big
what do you mean? For
difference.
each proof, there's their own power of tau, their own phase two.
There's different Z keys for each one, but still, that's only one thing, right? Like each encryptor now, like, has to have like their
Yeah,
own
each
things.
ciphertext will probably need a powers of tau.
But that's fine because we don't need to do a trusted setup for it. Like, okay, like I think it's fine if there's like an overhead of the decryptor downloading an extra GB of data. Like that seems like a great trade-off. And the encryptor uploading
Yeah,
an
I think
extra
it's
GB.
inevitable.
Huh?
I think like you'll have like a huge like if like anything would work, it would have a huge like communication thing. But that's like fine.
I think it's fine. Like a huge communication overhead is fine because the only thing that needs to be posted on chain is the actual like this single value. The rest of that stuff can just be like made DA
Wait,
available.
nothing
Like,
is ever put on chain. Like it's
or fine, nothing's on chain, but like the encrypted value is the only value that needs to like the encrypted value and these powers of tau for that specific set of the only stuff that needs to get made public by the encryptor, which is the same as our guarantee for Groth16 is, you know, the person publishing the proof needs to the person publishing the prover / verifier needs to make the Z key public and the verification key string public. That's it, right? And so I think this seems totally fine. Like we're already assuming like complexity of Groth16, which is that both like proof creator and or I don't know, yeah, the person who wrote the proof and the person proving the proof both like, or the person making the proof uploads a big p tau and the person making the proof locally like downloads a big p tau. Like it's the same guarantee. I think that's fine.
Okay, yeah. Or okay, I guess I can keep going. But like,
Okay, so
so
now
this
what's
is what
wrong?
I tried. Or what I like this is what I tried, right? So what you do is like you like the verifier computes like E of G1 alpha G2 beta times E of like L bar G2 gamma, something like this. You raise it to like some RS. Right.
Wait, sorry, stupid
And,
question. What's the difference between L and L bar again?
L
Like, oh,
bar
L bar
is,
is the evaluation of L at tau on G1. And then, sorry, why do we multiply by witness and gamma inverse?
wait, sorry. So L bar is public inputs and L is private inputs.
L is public inputs and L bar is private inputs.
These are both like G1 elements.
Wait, so there's P public inputs, or
Yeah, P is the number of public inputs.
P is the number of public inputs, and so L is for the private inputs and L bar is for the public inputs.
Yeah. L is used for proving, obviously. L bar is public.
L is used for proving. Fuck, where are we using L for proving again? Because when the prover calculates C, they use all of L, and when you add the shit, sorry, I'm just refreshing myself on L. When you Um. Uh, Wait, sorry. Groth16 is verifying A times B minus C is H times a zero polynomial, but uh, L is uh, A times B minus the vanishing polynomial. Oh, which gives you C. Which gives you C.
Yeah.
Okay, right, correct. Okay, yeah, okay, got it. Right. Sorry, so this is correct. L is, okay, sorry, so L is A plus B plus C. L is A plus B plus C. And then we add the.
I don't think the details are that important, but like basically L bar is public and L is like private.
Yeah. L bar is built on like all the parts of the witness that are public. It's just like you split them up essentially.
Yeah, so I understand L bar versus L, but sorry, I'm trying to understand why L is like A plus B plus C and not A plus B minus C. And it's because
Wait, it's wait what?
Oh, is it? I'm not actually sure, but you should check that there.
or I think you're correct.
Wait, it's just
You're correct, but I'm trying to understand.
the minus is like not relevant here, right?
I think you think of L as like wait.
Like the minus here is either like dividing by the pairing or sorry, subtracting the pairing or adding the pairing. Using additive notation. Like that's not important. It's basically just like some weird linear combination of like A, B, and C.
And the point is that this lets you commit to A, B, and C via this like RLC kind of thing.
Yeah, in a way that like cleans up the check. The check becomes really succinct because you've like sort of combined them together. Is my
Right, in the sense that you kind of get rid of the like A and B values by multiplying out the tau values, and you're left with only C at the end.
What?
Or something like that.
No, that didn't make any sense.
Wait, sorry, because here we do wait. Sorry, I'm trying to understand this like C calculation that the prover does based on L, A, and B, and the vanishing polynomial. Good.
I don't think this is super relevant. Like it's just sort of like again, Groth16 does not have a lot of clear intuition for why it works. Like Remco says this in the post as well.
Yeah.
He's just sort of like the shit just clears up in a really like pretty way. It's hard to separate out into clear parts. Later systems based on polynomial commitments have much more modular structure, like Planck, for example.
Yeah.
But I think there's just like some cleverness in how different like random points are used. Yeah, I've never gotten like. Okay. Okay, the other thing I'm trying to figure out is like, so there's also this like functional commitment paper that essentially like does witness encryption for functional, or it does witness encryption for functional commitments, and like one of them is based on like Groth16 verification. So I'm wondering like, are we just gonna like eventually just rederive this?
Like the Litma FCI paper or whatever?
Litma.
Something like that.
Yeah.
Litma Pavlik, this one.
Yeah, Litma Pavlik.
It feels like we might just be slowly moving towards.
Are you
this.
sure? Because that's just for functional commitments. Like the Litma Pavlik is not a witness encryption on the functional commitments, right?
That makes
I don't understand it.
that makes a functional commitment based for like a large class of circuits based on Groth16, and then this paper by like Dario 4A or whatever, you like their construction for witness encryption on functional commitments
Uses
like,
that.
take in their thing. It's like one of the things that it can take in. But yeah, I'm trying to figure out like, are we just doing this basically?
Express A and B as a sum of two elements where, yeah, you separate the secret and public data. Okay. And then what? Well, yeah, I think my big problem with this like Groth16 verification is that like because you're separating out the public and private inputs, you have to do like this additional step where you calculate stuff for L bar basically, but it's like right. So you have this extra pairing with L bar where that is directly calculated.
Wait, that's public. Like this is the V key. Like you already know this.
That is the V key, correct?
Like wait, Nathan, can you scroll up on your iPad?
Yeah. Where?
To like where you wrote the Groth16 equation.
Oh yeah.
Like this is like the V key. Like this part of the equation is like the left-hand side is the private part, but like this initial pairing here, like of E of alpha times this, you can just pull out, which is that G to the T to the power of alpha beta, and this thing you already know. Like
this thing is like some public value C, like some constant.
What's C?
Oh, sorry, so this is just some constant, like e to the L gamma G2.
Yeah, this is just a constant basically.
That is a constant, right? Okay, and so that constant is what he refers to as GT to the alpha beta, is absorbs that L term.
No, that's this thing.
That's this, but then sorry, this is that second term.
Yes.
And then where's the third term? Oh, that third term just got moved here.
Yeah.
Fine. Okay, I see, and this became a negative delta.
Yep.
Aha, right.
So these two things are already known. It's like these are the things that are like A, B, and C.
Right, sorry, yeah. Okay, so this is the place that I got to when I sent you the video, right, Nathan?
Yeah. Or like, I think we just had the Groth16 like pairing equation, basically.
Right.
Okay, should I like
sorry,
go
continue,
on?
yeah.
Or... Okay, yeah, so basically like my second idea after like the thing I sent you was like we just do this.
Wait, sorry, so the reason the first idea doesn't work is what again? Oh, because
the first idea is like the same thing as this, it's just like with one exponent instead of two.
Okay.
And this will not work. But I'll just like do it anyway. And so like this like so like the verifier like computes this, and the verifier also has to send like a bunch of powers of stuff. Because like basically the idea is that we want to like have the person compute something like this, right? Or RA-SB times E of RC SG to the negative delta. Like we want them to, sorry, this, I'm mixing like additive and multiplicative notation.
I mean, I understand like SG to the negative delta means like you're putting S in the exponent. Yeah, sure.
Okay, yeah, so we want them to like compute this. So to like compute A to the R, we're gonna give them a bunch of terms that look like G1 to the R, G1
right,
to the R,
and then for B you give them G2
and so
all
on.
the way to the...
We also need to give them like G1 to the alpha R and G1 to like the delta R or something. And so same with like B to the S, we give them like G1 to the S.
Right, and then to be able to calculate all the terms inside of C.
Oh, sorry, I'll use G2. Wait, sorry, what?
Yeah, and this lets them calculate like the full values for A and B because now they have like the SRS for each of the terms.
Yeah, and you do the same for C. But now this is kind of just a big problem because we just gave everybody access to G to the G. If we pair these guys, everybody just got access to this.
GT to the RS, T to the 2I, right? Oh no, T to the I because he's
it doesn't matter.
Right, yeah, you're right. Okay, so what's the problem with
and
this?
Like, well, like the entire like constant right hand side is just a polynomial in tau because it's like GT to the alpha beta. Okay, this guy can compute like this from like this and this, right?
Yep.
And then times like E of L bar. This is a polynomial, and this is just like whatever, right? We already know this. Or I guess like
pairing on the
if you
right side
expand
of
this,
you mean?
this is just this pairing value is GT to the sum of like WI LI tau.
Right, yeah.
And this is just like GT to some like poly and tau. And when you raise this to the RS, we can compute everything using this.
Yep, that makes sense.
So
Sorry,
basically just
but
like,
you don't know L, right? Like L
You do know
counts.
L.
L bar is public.
L bar is public because the public inputs are public, and so people can just manually calculate. Sorry, this GT you say is on L bar or on L? Oh, it's on L bar, right? Because it's 1 to P. Okay. Right, so everybody can calculate that because they can just manually calculate the exponent that each of these terms, these GT terms, should be taken to based on the value of L. Okay, got it. Okay,
Yeah.
so then the question is, how do you prevent this?
Well, I don't know. I think this scheme is just broken this way. So like this will not work. I don't think anything similar to this will work either.
Yeah, I agree.
And I guess you could also say like Li tau also has terms that look like theta tau to the I times like RS, I guess. But like because of this, we also get, if we like combine like these terms, then we're also gonna get like GT to the theta RS tau to the I.
Right. Yeah.
So like you can compute everything, I'm pretty sure. So this just does not work. And like this is like kind of the reason why, like, because like this right hand side is like public and it's some like, it's not a V key, which is G to the X for some like secret X. It's just a full on like public polynomial in tau. It's just computable.
Right.
Why do we reveal L bar then? Like, can we just reveal a commitment to L bar instead? Like, we add an extra exponent on the right side on that last pairing, and then we reveal only the. Oh, but then how would someone know they have the correct proof? Because basically what I'm thinking is if we hide any of the elements of L bar, then the person cannot compute everything on the right side.
Yeah, so this is actually my idea. So, and I'm not sure if it works. I don't think it works, but I think it could like be a bit helpful. Basically, like my idea is we
Did you get that?
augment the circuit to include an additional dummy constraint. We introduce a new variable like W0, and we're just going to introduce this constraint.
Right, exactly. And then the idea is that as long as
and this guy will be public.
Oh, that's public? Wait.
However, or it's a public input, but we will not tell.
Correct, yeah, exactly.
Anybody.
We don't tell people what this public input is, but it's still part of this like L bar summation, and you have to know this value in order to compute the like.
And it'll be like sampled randomly. And right, so now like the value, so now the term on the right hand side, which is like this guy.
Right, exactly. So
This
W0
like
becomes part of L
truly
bar, right?
random.
Is what you're saying.
Yes.
Yeah.
So this W0 becomes part of this thing, and we publish this value, and this value should like look random.
But we publish W0.
Sorry?
We publish W0.
No, we publish this pairing value.
Oh yeah, okay, yeah.
Or maybe like raise to some power or whatever we're doing.
Sure, yeah.
But basically like we're baking in this dummy public input into our circuit to make it look random.
Okay.
Or like, okay, wait, I guess you can think of it, or like I thought of it as like I'm randomizing my circuit basically.
Your what? Your circuit?
I'm randomizing my circuit because I'm adding like a random public input that doesn't make any effect on it.
But then how does the person actually computing the witness get this value?
So that was what I'm not sure about. So I can like do some more stuff. Basically, like using from this constraint, you get some more stuff. Basically, why do I keep on doing? Okay, you have like these polynomials related to it, right? These are both 0. And this polynomial is like
Wait, what? These are both
1.
0? Sorry, why is that 0?
Because like this is 0 and this is 0.
Oh, I see. This is just the first term. Okay, got it. Yeah.
Yeah. And this A0x is like it's like some non-zero poly. I think it's something that looks like this.
So it says
or some shit, whatever. It's like
it says
it's
what,
basically
x to the
like
n minus 1 minus x over x minus 1.
yeah. Or you shouldn't actually believe this. This is like on a specific domain. But basically it's like 1 if like x equals x star and 0 otherwise over the domain.
Sure. Yeah.
Right.
Wait, X star is like W0 here?
X star is like whatever index, like, because you have like your like constraints, right? Each like row is a constraint. And in some row, say like the last row, you're gonna have like this constraint. And then like your rows are indexed by the domain. So this might be like omega to the 0, omega to the 1.
Yeah.
This could be like omega to the or I guess like m minus 1. So like it would be like 1 on this value and 0 everywhere else.
Yep. The basis.
Okay,
function.
so basically like these values are all like, these polynomials are all like public and they're like very simple, which is kind of nice. I don't know what to do with it, but so like my idea from here was that this is kind of where I got stuck basically, is that you choose like a random W0 and you're gonna publish, say like this value, like the right hand side. And like also you obviously like send like your public inputs, but not W0. And then somehow we want to send values that look something like G1 to the W0 times like some like blinder, such that anybody with like a proof, A prime, B prime, C prime, can like augment their proof using these values into A, B, C, such that
That includes W naught.
yeah, so we're augmenting these, like this proof is like because obviously like any like set of inputs that works with the original circuit also works with the augmented circuit, right? Because like this condition is just like useless. So basically that person is going to generate a proof without this constraint because they don't know W0, so they can't generate a proof using this circuit, but they can generate a proof using the original circuit. So they're going to generate this proof, A prime, B prime, C prime, and then we're going to supply them with some helper values, which are powers of omega, or powers of W0, sorry. And then these values should not reveal W0, because once you reveal W0, you're basically dead.
Right, because you get back to the original situation.
Yeah, because then anybody who knows W0 could just like compute this like constant, right?
Yeah.
So these values should not reveal W0, but it should allow somebody with this proof, A prime, B prime, C prime, to augment their proof into A, B, C, such that like they can compute this like pairing, and it will equal like what we want it to be equal to.
I see, because this like provides a level of separation on the right side in the sense that everything's not public, so you can't like reverse engineer that, but it also allows it to be like a meaningful part of the witness in a way that you need the rest of the witness to be able to construct like the full ABC.
Yeah, so like
I see how this is
you can
promising.
kind of think of this as like the analogy, right? Because like now this is kind of like your V key, which has some secret baked into it.
Which is W0 basically.
Yeah, this is W0. But like my intuition is that the main problem is that you're not really, or you're raising it to the power of X, but like, or you can think of this as like, maybe have like some completely public value, like G to the P, where P is some public number, and you're raising it to the power of X. But in our case, we're not really raising it to the power of W0, we're like multiplying it by G to the power of W0. And this is like a lot harder to handle. That's my intuition for, like I tried a bunch of stuff, and I couldn't really get anything to work, I think.
Right.
So wait, why does this not work in the end? Sorry, I missed this very last part.
Or I guess we can kind of like see what we would want to do, because I didn't like I kind of like rushed through my calculation.
I'm gonna ask you to move outside.
Okay, so like let's just like see what happens. So first, a prime of x. Oh, sorry, Vivek, were you following the everything I said before? I can just like keep going.
I think so. So I think wait. So some parts I'm confused on. Wait. So this A prime section. So this is basically a witness that doesn't include this like.
W naught. This is your original witness, basically.
And then what is the procedure to transform it to
Like
this
to
like?
add this W naught value to all of the constraints manually that you can only do if you have these original values.
Okay, so that's just public, like.
Bruh, why can't I join the Zoom?
Probably because you have 1%.
Yeah, you know what, that would check out. Let me close some stuff so that this can be faster.
It was beefy.
Yeah. Can you check if my stream is still running? I can just check if my stream is still running.
Yeah, I have no stake in this. I'd prefer if it's not running.
Yeah, unfortunately, we disagree. Shoot, we need to get the Zoom link back. Sorry. Right, okay, sorry, we're back. We are on 1% though, so it's like there's a non-zero chance we accidentally get yeeted again.
Okay.
But I think we should be okay for now.
Okay, I just had an idea, but I'll keep going.
So I think Vivek had a question before you keep going.
Well,
Oh
yeah.
yeah, sorry, go ahead.
Yeah, I'm confused at why this isn't just like basically embedding a
right.
BLS signature or something like this, or like if this is like
Okay.
strictly over engineered, then like there is a proof and that there's also like a BLS signature separately that you're encrypting to or
Right.
something.
I guess like I think most of the witness encryption that was seen is just the philosophy that we're like randomizing some public value, and then we're giving some auxiliary information such that anybody who knows the private value can compute this randomized value. That's how like BLS works, right? And that's also how the KZG witness encryption works. And I don't really know about the functional commitment one, but like, I didn't really read that one carefully. But I think that's like kind of our idea for witness encryption right now. So that is kind of what I'm trying to apply here. A very subtle difference is that in the BLS randomization, we're raising it to a random power, whereas here we are multiplying by a random power. Currently, not that it works, but that's like, I guess that's the philosophy behind it. Like, I think it is very similar to BLS over time.
We're multiplying by it, like this W0.
Yeah, so like, if we have like imagine like some public value P, this is like, say like hash of T in like, in BLS.
Mm-hmm.
then in BLS, don't think of this hash T. Just think about some public value. So in BLS, we're raising this to some power, R, some random power. Here, we're kind of like, okay, we just tried raising it to random power, right? Like we tried doing like this to the RS and we saw it didn't work. Maybe there are ways to do it, I don't know. But now, the way we're randomizing it is by doing this.
Right. Right. We're basically
so
just
this,
adding in this like W naught.
Probably worse, but we'll see. I like kind of had an idea just then. I'm not sure. I don't think it works, but I'll see. I guess that's how I'm thinking of it right now.
I guess I'm a little bit skeptical of this just because like the reason the raising it to the power of the random value is nice is because then you can like manipulate properties of the pairing, right? Like in that, like when you do pairings or other stuff, that multiplies out nicely. But tacking on a random value basically like as a sum in the exponent doesn't seem like it'll play as nice. Like there'll be like weird cross terms and shit like this.
I think it's still worth like bashing it out and seeing if we can find something maybe.
Yeah, I think we're deep enough in that we should keep going, but I'm like a little bit lost, I guess.
I imagine raising could work if you add sufficient randomness. Like if you add a lot of random terms, but it sounds very ugly.
Yeah, I also think this could work, but it also feels like there is some like weird impossibility thing in that like the right-hand side of this is public. And so like anything you include on the left-hand side to be able to get the thing on the right-hand side, like you could also just do directly on the right-hand side, if that makes sense.
Exactly.
I'm not convinced by that.
Yeah.
Why?
Because on the right-hand side, the only way you're getting terms on the right-hand side is by multiplying values in the common reference strings that you have together to get GT values directly. But the idea is that here, if you can provide a value where you didn't provide the corresponding value in your SRS, you might be able to construct a term only on the left side that you cannot construct on the right side.
But like, I guess like, how could you construct it only on the left-hand side when the right-hand side is like all public?
Because, sorry, the things on the right-hand side are not like, the full terms on the right-hand side are not public.
They are.
Sorry, the result on the right-hand side is public, and
all the terms involved are public as well. Like all the L polynomials involved on the right-hand side are public. That's why the RS thing didn't work before, because you could just plug those things into L directly into like Li from 1 to P and get everything.
But the only reason you could do that is because you had the GT values for like alpha, beta, tau, etc., like already exposed in the SRS. So you could combine them with the value you knew of L.
No. There's like, but we introduced these new terms, like not this RNS, or these are just one. But
sorry,
like
your new RNS.
New RNS.
Correct.
And you need those for the left-hand side to be able to do the left-hand side stuff.
Okay.
So they're also available on the right-hand side.
They're also available. No, but the only thing you have on the right-hand side is not right. Yes.
But again, this is a different strategy here where we're not raising stuff to the power, we're like adding randomness in. So yeah, let's just keep chugging along. I think we're either like, I think if my hunch is correct, we're close to figuring out why this doesn't work, but let's just keep going and like prove it.
Okay.
So yeah, B and B prime and C prime are the same because like those polynomials are just 0, right?
Or C is not C, because C is not related to C.
Oh, right. C is fucking
C is like
weird.
that giant, like, yeah.
But
so, like,
only,
this is actually,
but only
like,
one term in that is different, though. Oh, no. 2 terms are, like the L and the A.
Yeah. Or no, it's the H that's different. So, like, the H term is actually, like, this. And then plus, like,
the H is different. Wait, what are you doing?
because your quotient polynomial is different.
Sure.
I think, or wait, sorry, I missed the W naught.
Why? Why don't I just leave it here?
it's not that hard to check that this should be true. Okay, so yeah. So now we're kind of just stuck here because we want to give. So what do we want to give? Well, we want to add this guy to A prime, right? So we kind of want to give them like G1 to the W naught, A naught. We want to give them this. But this is problematic, right? Because the CRS includes G2 to the beta. So then they can just automatically compute this value that we do not want them to compute.
Yeah.
So there's a problem. So we could try some shit where we like give them, like we can randomize this, where we, oh no, we like multiply by like R or some shit. And then we also give them like G2 to the R inverse. Oh wait, this was my idea just then. So now they can, when they pair this, they get this guy, right? Or they get this guy. And you can't really compute this directly. So that like kind of works. But now we can do C. So we want to give like this giant term.
Wait, sorry,
And so
where'd you
an
get this
immediate
from?
problem here. Oh, sorry, go ahead.
Wait, sorry. Where'd you get this from? This exponent? Oh, from there. Right, because this is a diff on C when you add this A naught term.
Right.
Okay.
So immediately, like B is private. So
wait, sorry. Well, why do you
we're
have a
gonna
term
have-
that's A 0 tau times B 0 tau? Because you never multiply A and B, right? Like, sorry, where is this term coming from?
Yeah, it's a little bit more. Basically, like.
Oh, that's
H-
coming from L. Right.
It's coming from H. L does not change because L depends only on private inputs. So basically, H of X times Z of X equals A of X, B of X minus C of X.
Right.
And then when you augment this, so let's replace these all with primes. So when you augment this, you get A of X, B of X minus C of X. So this is equal to H prime of X minus W naught X to the X. So wait, what's going on?
Wait, isn't C of X
So-
different too? No, it's not.
Oh, sorry, I should have a Z of X.
This is really because we're mixing like the original A's with these new things.
Wait,
Right,
sorry,
yeah,
wait. Why?
Maybe there's
feels
a
off
plus
here.
term. Shit, I don't. Yeah, there should be a plus term. Wait. Okay, let's do. Sorry, it should be this. That's correct. And so now everything.
Yes, correct. Yeah. Okay, yeah. This is it. I see now.
So
okay.
basically, like H of X equals H prime of X plus.
Like divided by Z of X, right?
And you can just call this polynomial like the quotient P of X. So basically, when you're changing, so if you look at the term for C, it looks like H of tau times Z of tau, right? So if you multiply out, you're basically just multiplying out the denominator, so it just increments by like, this guy.
Yeah, I see. And that is Right,
So
because
that's
you
why we
multiply
have
through
a,
by z of x,
this term.
and so this is where the diff of the c comes from in this additional term, right? And then, sorry, scroll up a little bit again. That second term, w a naught.
That's because
that
A
is-
changes.
Right, exactly. That's from directly a changing, because our new c is gamma inverse times h of tau, z of tau, plus s times a of tau. And so now
S is 1, so it's just
s is 1, and so we're just adding the new a of tau value, which is exactly this. Okay,
Yep.
got it.
Yeah. Okay. Cool. Okay. So we want to give them this term, but right. An immediate problem is that B is private. So we have to feed them powers.
B of
Tau.
tau.
So, so how do we do this? I guess like we already kind of fed them like this guy, right? Like we already gave them this. So we're gonna try give them something that looks like.
So we gave them that by giving them g1 to the w naught a naught tau.
By giving them these
Yeah,
two.
exactly. By
But
giving
this
them
is
these two
R,
values,
sorry.
right?
This is
Okay,
like
so yep,
new
yep,
random.
I got it. Okay, yep.
So this failed. This is like take for now. So we have to give them like so on. Okay, so now it looks like we're good. Except we're not.
Wait, but I'm confused. They need g1 to the power of this thing, but if they tried to get rid of that r by doing the g2 combination, they already jumped to gt. So how does a prover get this value in g1?
True.
Sorry, what?
Like to get rid of this r, you have to jump into gt, right? Because you have to multiply by this g2 value you gave. But the value you need the prover to compute is in g1. So how do you do this? Like how do you get rid of the r in g1?
Works.
Like,
Yeah. So this doesn't work. Or like we want something like this, right? Wait. I mean, what you could do is you could like add this randomness instead. This doesn't work, but you could then like give some more terms that like let you cancel out the randomness. Something like this.
you add more terms to let you cancel out the randomness. Sorry, I'm not understanding how this helps cancel the randomness.
Because basically they're computing like you have A times like G1 to the this. They're like, hey, what happens if we do times R? I'm just curious. B times like
This
oh no,
is
like I'm just gonna call this value like X for now.
this is like slightly unrelated to this current direction one, but another thing that seems promising is the malleability of proofs. Like the fact that you can put in some random coefficients, or sorry, random multiples and still get
Yeah, the problem is it doesn't. But you're not changing the public value. Like for all of these, the public value is not changing, right?
Yeah, like would you just multiply, like when you do the malleability.
Like you're just changing the proof elements.
Yeah, my impression for the malleability is what happens is that all of your values are the same. You just multiply all of A by like I don't know, Y, and multiply all of B by Y inverse, and you get a new value, like a new set of proof values, but they're fundamentally calculating the same pairing because Y and Y inverse just cancel out. Like when you calculate that pairing, right? Because you get Y inverse in the exponent, in the combined exponent, which is 1, and then it's the same proof eventually. So I don't think malleability is like super relevant here, right?
Trying to think if like
Okay.
there's something you could.
I'm not sure where this actually goes. I might like take a look. But basically, if I gave you like plus R, then I would also give you like, I would want to do like G2 to the minus like RB of tau. Or yeah, something like that. And to give this, I need to give something like G2 to the R, G2 to the R tau, and so on. Maybe like G2 to the R beta. I think the long story is that like, whatever values I'm giving you, you can always pair them up. Because like, if I give you like some G1 value here and some G2 value here, and then when I pair them, I get like E of A prime, B prime times like some GT to the, GT to like some power X. And then I also give you some, if I also give you some like G1 value and some G2 values such that when you pair them up, you get like E of C prime, G2 to the negative delta times GT to the Y. Like, you're forced by the like equality that like GT to the X plus Y equals like GT to the beta W naught, tau. So like anybody really could just pair the elements themselves to compute G to the X and compute G to the Y and then just add them to get this value. So I feel like this probably never works, but I'm not sure. That's my intuition for now. Like you're kind of forced. So like one thing you could try is maybe you only give them G1 values. Or maybe you give them a lot of GT values because then you can't pair stuff, right? You just make sure you give them like good enough like G1 and GT values. But I don't know if that's possible.
plenty. I think I have some other work I want to finish today. But this was very fun. I feel like I've definitely gained a lot more intuition for why this can or can't work.
Yeah.
I'm not convinced. I don't think I have closure on why.
I
A
mean-
modification of the proof would absolutely not work. Although I have more intuition, I agree.
I think this is just rough intuition of like with BLS signature witness encryption, what's going on is like there's like some private, like well-structured value that itself is kind of based on another private value that like doesn't really exist in the proof structure. Like there isn't kind of like this two-layered private value thing, and so we're trying to like build in another private something, but that kind of just seems like it either can be broken or like just kind of becomes the signature witness encryption at the end of the day.
Oh, I see. Because the whole thing in BLS signature witness encryption that if the signature is public, then anybody can decrypt the message. But here we're trying to come up with a way to make the signature public, but somehow combine it with a witness so that even if you have the signature, you need the actual witness to be able to decrypt the message or something. Or maybe that's not exactly it, but at least
Not quite. There's like something in there that was wrong. Like, yeah, I think the way I'm thinking about it is like there's basically like there's like in signature witness encryption, the reason it works is there's like a private key, which is like super private, and then that can generate a signature, which is also private, but it is like structured enough that you can kind of like encrypt to it. Whereas like in this case, like in my mind, the proof and the witness are kind of the same. Like you could just generate a proof from the witness. So there's no like extra level of like hiding kind of, but I guess there is in that the proof like in the ZK form like hides the witness. So it is like structured from the witness in some way. Yeah, I wonder if making R and S1 is like potentially screwing this.
well, the point of RS
Yeah, I was
being
thinking that because I feel like you want more randomness. I feel like that would be important. So I think you might need to like use RNS, but
Because then you get this structure of like, okay, so to map it to signature witness encryption, there's like private key, signature, encryption. And in this case, you have witness, proof, which is sort of hidden from the witness with this random values, and then encryption based on the proof. So at least the high level structure is still there, but again, like how it all clicks together is a bit weirder. Because yeah, there's kind of another thing here where like the verification key structure in signature witness encryption is also based on some private input, the same private input as like the proof. But kind of by the nature of ZK proofs, the verification key here is like not tied to a specific like witness, if that makes sense.
but it's tied to the public L values, which is the equivalent.
No, but those are public. The equivalent thing here would be like that it's based on some private thing.
So the thing that is binding you here is like a set of private values that satisfies the relations in A, B, and C.
No, but like in this doesn't bind the V key. Like the V key itself, its structure is not based on like some private input. The V key is just, it's all public values. Like the way you actually verify this, or like.
So that's
Kind of
Nathan's
use it.
prediction, right? Is that if we now add this value to the V key that is like based on some private randomness, and that gets thrown into the V key and that gets thrown into your SRS, then maybe there's a way to simulate that like kind of thing existing.
Right, but it seems like there's no way of doing that that doesn't also like reveal that hidden thing, because like all the values in the V key are public.
Well, I think the idea that I'm thinking is like, oh, like you reveal that hidden value, but that hidden value is useless unless you have satisfying instances of like the rest of A and B that you can use to multiply together with it to be able to get the correct terms on the left side.
Okay, and you get that, and then it seems like you can just unlock it on the other side then.
You can unlock it on the other side because if you have that value, you can potentially just multiply by the right values in the SRS and just reconstruct it on the right side as well.
Yeah.
Yeah, so then the question is like, is there a way to give like I guess the like key question here is like, is there a way to give a subset of terms that can only be calculated on the left side and not the right side? And like, it's not clear to me the answer to this is no yet. Although intuitively, like the very basic things we've tried have failed.
Yeah, this sort of like hidden witness thing seems promising, but like also seems like,
I mean, I agree. It feels like it's breaking some simple property or some simple invariant or something.
yeah, like it doesn't work for some reason.
But I'm just not mathematically convinced yet. Like, also pairings don't seem like they work. So like something here is like, my intuition is a little off.
Well, yeah, because I feel like it'd be nice to like experiment with like, because like a BLS signature is like the most simplest, like, I guess even like KZG is like the simplest like pairing equation you can have, right? But Groth16 is like a pretty, I mean, it's not that big, but it's like a fairly complex like pairing equation. So if there's like some middle ground that we could like first establish and like maybe construct for, then that would be really nice. But I don't have anything that comes to mind.
Yeah, that's a great point. Like, it'd be nice to sort of work our way up here. So what is like in between like a KZG commitment and this? I wonder also if there's any sort of like kind of degenerate proofs, like degenerate Groth16 proofs that kind of simplify some of these equations. Where like, I don't know, fucking C is just, no, C can't be 0. Like B is 0 everywhere. And then it becomes a lot like simpler, but then maybe you just can't actually implement anything interesting with something.
But that's a good question. Like, I want to simulate this with the Groth16 proof that x times y equals z or something. Like, just a single prime factorization is all we're doing here. And then I just want to like...
Yeah, that's what I did like up here, right? That was like the first thing I showed you guys. What was it? Like this thing. Or this thing. Oh wait, no, I scrolled way too far. Wait, what?
I think it's a bit further down, like the RS thing.
Yeah, this guy.
Yeah, but I'm saying like I want...
So I haven't like... Yeah, sorry.
No, go ahead. The thing I was saying was like I just want like A to have one value and B to have one value, and we go from there. And that way I can actually deal with vectors in my head instead of like polynomials and stuff. But maybe, sorry, maybe explain the thing you were going to say.
Or I don't actually know what I was going to say. I think like... Or yeah, I was going to say that I haven't proved that that's secure. I'm just like, it just feels secure. Wait, so you're saying like you have like A, B... Or like, I mean, the problem is like examples that like look like this are like trivial, right? So we need like some sort of additional constraints.
This is an interesting note.
Here's like...
Oh, sorry. Just really quick, one of the notes that Remco makes in his post is like, instead of providing alpha times G1 and beta times G2, we could also directly provide alpha times beta times GT, which he calls G3, in the verifying key, but G3 elements tend to be big and weird, so we avoid them. And so I wonder if we could do the thing in which in this Groth16 verification key, we try to provide a minimal number of G2 values. In fact, ideally 0 G2 values, and we only provide GT values and G1 values. And then maybe this way we can avoid somebody using our G1 value, combining it with the G2 value in our SRS and getting this GT value that we don't want them to get.
That seems promising.
But that's actually what I'm doing right now. Where like, basically I'm, like we wanted to give them like, we want to give, them like this guy, right? we want to give them this. So like I'm gonna randomize it or I raise it to this, and then on the other side I'll give them like something like this.
These are both on G1.
And then you get a shit ton of cross terms, right? So
Sorry,
I'm only gonna
G is
give
what here?
them
Wait, G is G1 or?
yeah, like G1, G2.
Okay, yeah.
So this is gonna like generate what I want, but it's gonna get a shit ton of cross terms, right? So my idea is we only give them GT cross terms. And then as long as these GT cross terms are like not gonna like be linearly dependent or whatever with like the value that we don't want to leak, then we should be good. And that like should feel true, right? Because all these have like some randomness baked into them. And so this like would boil down to like some polynomial or some shit, or some like polynomial like linear independence. Okay, I haven't actually like looked through this carefully, but like, yeah, that's my idea. Like we just give them a shit ton of GT values.
Okay, but then how does the prover construct all of their B values? They don't have all the like necessary G2 values.
They don't need them because they just need this value to multiply A, this value to multiply B. They pair this, they get a GT number, or they get a GT point, and then they use all of the GT points that we give them. They like add and subtract these terms, and then they get, or they do this to cancel all the cross terms, and then they're done.
Interesting.
Oh,
This
interesting.
actually seems pretty promising.
Oh, would this work? Oh. Sorry, keep going. We like disturb you.
Keep cooking.
Yeah, I don't know where this is gonna go. This is just like a shit ton of terms from like whatever. I don't know. But yeah, this feels like this could work, but I also said that about like at least 3 previous attempts.
This is how research happens.
Yeah.
Just kind of keep delusionally saying this until it actually is true.
Wait. Okay. So
Yeah.
eventually, the goal here, just to remind myself, is like someone with a valid proof plops out with
This like little hidden value, which is the thing we actually like encrypt to, basically, right? But if you-
They should never really, okay, I guess they should get this hidden value, but it should be as a result of like some magical computation that works because of what they have.
like only someone
Or
with a
it
valid
should
proof.
work because of this pairing. Like the values A prime, B prime, and C prime should not matter. It's purely, this is like the weird part. Like these values do not matter at all because at the end of the day, we're augmenting them. And like, it's the augmentation that actually matters. It's just the fact that we have this pairing. It's like that we have this multiplicative relationship that's really important. Like, but at the same time, this feels really weak, right? It feels like we're not utilizing like everything that's given to us. So like, that's why I'm also a bit hesitant.
Wait, I'm confused at why these things don't matter. Like,
Yeah, I'm also confused.
Or okay, basically like we're trying to leak this value, right?
mm-hmm.
And like the way we're doing this is we're utilizing the multiplicative relationship of pairings, where we can give you G1 to the X and G2 to the Y, and you can come up with GT to the XY. And so, oh shit, wait, what's going on? I think like, or I guess like we are actually, okay, that was a lie, sorry. We do need these A prime, B prime, and C prime because we need it to evaluate these cross terms. However, apart from that, So you could
sorry.
think of it as saying that we need the witness values, really. Like the A prime, B prime, C prime elements themselves do not matter as much.
Sorry, and this is correct or wrong, and they don't matter because fundamentally what these values provide is that it doesn't matter what like A prime and B prime actually are as long as A prime times B prime equals C prime or whatever. Like as long as you have a satisfying witness, then this cross term cancels out and gives you back your like C prime term that you already know, but it's kind of like it's the same as the rest of Groth16 basically, in which you don't actually care what these values are. You just care that when they multiply out, they will cancel out your eventual C term or something like that.
Yeah.
Yeah. But then the problem is in any scheme in which they do matter, because you need to multiply by this like special random value, the problem is you don't actually know A prime and B prime. You only know the property that A prime times B prime is like C prime. And so you can't do anything that relies on knowing just the other value in the cross term basically.
That's why, like, I feel like, or wait, I don't actually know if this is true, but like, can you assume from knowledge soundness that like somebody who has a Groth16 proof also knows the corresponding witness? Is this like allowed or like?
Someone who knows a Groth16 proof also.
No, because people publicly post the in the on-chain case, no, because someone will just post the proof and then the whole world will verify the proof, and then now everybody knows the proof, but they didn't know the original they didn't know the original witness. I think what Groth16 gives you is the first person to post a proof needs to know the original witness.
Yeah, there's also like malleability, so you can like take a proof and modify it into a valid one without actually knowing the witness.
Exactly.
Wait, so then what is knowledge soundness actually saying?
That is a fantastic question. Let's pull up that Groth16 paper.
So, I'm gonna leave the call on my computer and rejoin on my iPad.
Yep. See you in a sec.
Strengthening the notion of soundness we call set of proof an argument of knowledge if there's an extractor that can compute a witness whenever the adversary produces a valid argument. The extractor gets full access to the adversary state, including any random coins. Formally require that for all non-uniform polynomial time adversaries, there exists a non-uniform polynomial time extractor XA such that I see. It's like, yeah, it's the extractability thing where like if you have full access to the adversary's state, then you can get the witness. But how does this fight against malleability? Like as an adversary, I take this other proof and I fucking make a new proof.
Oh, the nullifier, right?
What?
Like the key thing here is that like because it's fundamentally the first person to ever post the proof, knowledge soundness. Wait, why is the nullifier important?
Well, they have a new thing. I didn't know that.
Oh yeah, Claude just upgraded.
I like this. This is kind of fun.
Yeah, it's cute.
It's like CSS drop shadow equals 5. So trivial. Okay, nice. Today let's just make strong assumption about the adversary in this vector.
I think the original paper defines it with respect to something like affine provers or something. I don't actually know what that means. But
Wait, what? But how?
this just feels wrong, right? Like, how if I just transform something with TNS and I know nothing about the witness, how can you extract the witness from me?
Because the idea is that the extractor knows all the public values, including the previous unmalleable
Right,
proof.
before the proof was made, he knows that whole setup of things, or whatever.
Or sorry, he knows the adversary's public inputs, which is the existing proof as well.
Right, okay, so it kind of is like a recursive thing.
And so the idea that the extractor should be able to tell, like, hey, this proof I saw previously is the same as the adversary's proof I saw newly, and therefore, because I can match the nullifiers and both are the same, I can extract the witness because I know it corresponds to that other proof for which I knew the witness. You see what I'm saying? Is that like the thing connecting these two proofs? The reason the adversary can connect the reason the extractor can connect the adversary's new proof and that old proof the adversary used is because he can use it, or they can use a nullifier to connect these two proofs. Or else they wouldn't be able to multiply and check. Because they wouldn't be able to iterate through all the values of like y and y inverse. You get what I'm
Yeah,
saying?
I think that makes sense. It's just kind of interesting wording.
Yeah, it's weird.
Because it feels like malleability should break this, but I guess it's just kind of like a strong thing. It's like the extractor knows like all of the previous states. He's like, he knows your state, he knows the previous guy's state, he just knows everything. That doesn't even feel like that strong of an assumption either. Or like, why is this interesting? Oh, I guess it's just that like, with all the information that an adversary has to generate a proof, I can also just do the same thing. Like there's no like hidden thing or something in there. Whatever, it's fine. This just doesn't seem really relevant. Aline.
I think like another
Why did you
like
say
big
Aline?
question that I have is like,
Those are three fucking rules.
how do you even like define witness encryption for Groth16 proofs? Because like I guess like the original definition of witness encryption just says that messages under false instances are indistinguishable. But like in our case, I don't even know if we're considering false instances. And even then, I think people like, wait, I swear like every paper that I see has like a different definition of like witness encryption. Like some have like some sort of extractability. Sometimes it's like extractable on something else. I just like don't know like what exactly we're trying to like define here.
Is it that someone with satisfying witnesses for A, B, and C are able to then read the message? But if, sorry, this is a very okay, so then what does this mean in cryptography land? Like,
Wait, is it true that if we can do this, like we've just solved witness encryption? Because then you can just say you.
And that's what I was asking. Like I feel like you could just bootstrap it with any like NP like
yeah, exactly, because
encryption and NP problem.
yeah, because Groth16 covers NP.
So it just feels like this is like.
That's why it feels impossible.
Just like by proof of other smart cryptographers have been trying to solve witness encryption. If this works, then we just solve witness encryption forever.
Does it actually though? Or like
No,
like we have it for an NP like or we have it for a language that's like Groth16 proofs. And then if you wanted to construct some other witness encryption scheme for some language L, like what do you do?
Say that again, sorry.
I guess you could. Yeah, I don't know. Like this is why I feel like this seems this should be like very hard. But
Yeah, it just sort of seems like, yeah, you just first make a proof that you have an instance, like that is sort of like your commitment here, or sort of like your witness, and then you encrypt to that proof. Like this seems like the same thing.
BLS witness encryption also seems like impossible to me.
Like signature witness encryption?
Yeah.
This is fucking trivial. I think
That's-
another piece of context, or like another like thing that's clicking for me now is like with both the KZG and the signature witness encryption, you're doing it on like a very specific element or like sort of like input output pair. It's never like like I have a valid signature, can I just encrypt to that? It's like I have a valid signature on a specific message, or I have a specific KZG opening at a specific point. Like in each of these cases, it's kind of like indexed on a specific thing, but what we're doing, it's not like indexed on anything.
Wait, it's indexed by the public inputs.
Yeah.
It's indexed by the public inputs, but like in the same thing could be true for like KZG and signatures. It's like the public input here would be like the public key. I have a valid signature for this public key, or I have a valid opening for this polynomial commitment, right? Like,
Or wait, like you can think of like, I think you can like first like fix a circuit. So you fix like your AI BICI,
yeah,
and then you can also like imagine that you fix some CRS, I guess. And then now you define an index on your public inputs. So I'm going to encrypt to like these public inputs, and then anybody who has approved for these public inputs is like good.
this still feels different. Or like, okay, maybe here's another way of saying this. Like, it seems like a prerequisite to something like this is to have a more general KZG witness encryption, where we can just be like, I have a valid opening to this polynomial, can I encrypt to that? Not like a specific opening. Or do these still feel like separate problems?
I have a valid KVG opening group.
Like the public inputs here.
So you're encrypting to some polynomial, some committed polynomial.
Yeah, exactly. Like if someone knows any of the values in that polynomial, they can decrypt. Like, this seems like an easier problem than Groth16.
So that's like our thing where we're encrypting to. Okay, so you're encrypting to like the like polynomial coefficients, I guess. That's
Yeah.
the equivalent that we're encrypting to public inputs.
Yeah.
Wait, or I feel like it's, and that's the kind of malleability you're talking. But you can't. No, wait.
This is unrelated to malleability. This is sort of like trying to
Or
generalize
yeah, you can't.
some of the existing witness encryption things, because those all seem very like pointed. It's like signature at a specific message, or KZG opening at a specific point. It's like the broadening versions of these are like, I have a valid signature in general, or I have a valid opening in general. I guess like maybe the parallel here for proofs is like, maybe it's really easy to make a witness encryption for a circuit that has only one solution. Like there's a fixed private solution. That seems like a lot easier to do than like making witness encryption for a circuit that can have many valid inputs. You know, like if you have a circuit that's like, I know a valid RSA signature, like from a specific public key, there's many inputs that could work. But if it's like, I know a valid RSA signature from a specific public and a specific message, there's only like one answer to that, right?
I mean, I think I understand your intuition. I understand that it feels impossible because you're kind of making this crazy jump. But I guess my like counter argument on the feeling is that it feels like Groth16 made that same crazy jump from nothing to, oh, now we can do this on like an arbitrary like set of arithmetic relations, where as long as A and B cancel out and give you C, you can like.
Wait, like ZK and witness encryption are totally different. Like we could do ZK proofs on a polynomial opening, like on any polynomial opening before. Like that is a thing we can do.
So then what did Groth16 unlock?
Well, first of all, so we also had R1CS. Like Groth16 is just a nice simplification of a lot of things. Like we already found a bunch of techniques to like make a circuit of a general like NP computation and then make a succinct proof of it. Groth16 was not a big step up there. It was like a shrinking of things.
Now the idea we could remove a bunch of complexity and make this practical. But previously we had like full constructions for MP or whatever.
Yeah, and this like uses a ton of ideas from all of those things to make Groth16.
I see.
Like the thing, okay, maybe like we can come to consensus at least on one point, which is that like if we can do this for a general Groth16 proof, like we should definitely be able to do this for like a general KZG opening. Like I prove that I know any opening to a KZG polynomial and I can decrypt a message, right? Like that seems like a strictly smaller problem than a like general Groth16 proof, right?
That's good audio. Wait, sorry, what you saying?
Like, okay, so yeah, kind of in the realm of like, what is a problem in between this like KZG opening witness encryption, which just came out, to Groth16? Like, an intermediate problem here is like, I want to encrypt a piece of data to any valid opening of a specific polynomial commitment. Like, it could be at 1, 2, 3, 4, 5, 6. You just need to know a single opening. Whereas like the current scheme right now that was published is like, I know an opening such that f of a equals b. Like you know both an input and an output. Like that is what you're encrypting to. And they use this for a really cool thing with like laconic OT. It's like the perfect tool. But yeah, does this seem like an intermediate?
Yeah,
I think like, yeah, wait, because it's kind of like, okay, this is like a dumb analogy, but it's kind of like Groth16 where like, okay, in Groth16, you're giving 3 elements. And like in your KZG thing, I guess you can also think of it as like you're giving like 3 elements, right? Like you're giving like your proof pi and you're giving like A and B.
Right.
And then you're checking some relation on these values, which is exactly what Groth16 is doing.
Yeah. I think that is a good analogy. I think it's like, well, there's like a shit ton more complexity in Groth16, and you can all of a sudden go to NP complete shit. Or sorry, everything in NP or everything in NP.
Yeah, something like that.
Something like that.
Like
I
Groth16 is expressive enough to embed any MP problem. Except
Or
like solution.
R1CS is like NP complete.
Right.
Yeah. Right, as in like the solution for an R1CS is like an MP hard problem if you only know the coefficients.
Yeah. Yeah, so I think basically like a first step to getting to this is trying to either do this KZG thing or prove that it can't be done. Because I think jumping to Groth16 is like, there's just so much added complexity that like makes things really difficult. But this seems like a much more constrained problem to try to solve.
Yeah, wait, so you're just checking like this pairing holds.
Yep. With like some G's in the bottom, yeah.
Wait,
Sorry, this is KZG.
wait, where? Wait, where do you need more G's?
Or like it's G to the power of like f of tau minus beta, right? Like,
G to the...
or it's like pairing of G1.
Oh, yeah, this is like a KZG commitment.
Oh, got it. Okay, sure.
Wait.
Interesting. This is basically just Groth16, except with like a lighter or an easier equation.
I think I recognized your voice, but I wasn't because I was sitting after.
Are they talking to you?
No, I just thought.
What?
Okay, there's just a bunch of noise in the background.
Yes, sorry. My AirPods died.
I see. Yes, I think it's like there's like a bunch less pairings. Well, I guess actually in Groth16 there's also just 2 pairings because one of them is like a constant term basically.
Yeah. So like, yeah. So I guess you kind of have to like move it to one side.
Pulling up the donk red post.
I know. Oh, I keep forgetting.
Okay.
But dude, actually, like every time I look at the Donkard post now, like I like get back up to speed in like a shorter amount of time.
Nice. Learning.
Which post?
Like every time I like look at KZG, I have to like skim Donkard's post again, and then I'm back up to date. People forget
Yeah.
what it is.
Is this like G or 1? I don't even know. G? Wait, no, it's 1. Wait, what?
No, it's GT, or it's GT to the 0. Yeah,
Right.
so it's wait.
Wait,
Yeah,
so what is it? Wait,
It's just
It's 1?
identity. It's 1. Yeah. Wait. Is this correct?
I guess it's the same problem that this is like a constant number, so you have to like randomize it something.
Right.
Is this even possible?
Well, if this isn't possible, then we should just give up on Groth16. But it seems like we need to get here first. Okay,
Yeah.
I feel content in reducing this to a simpler thing for today, and getting a bunch of intuition on witness encryption. I have a bunch of other work I have to finish, but this was very fun,
Yes.
and I'm gonna keep thinking on this.
I'm personally down to keep jamming. I don't know, Nathan, if you have stuff to do, but
What the hell? Oh, sorry. I don't know. Just a weird pop up. Yeah, I'm probably gonna take a look at the thing that I wrote up and see if it immediately fails. If it doesn't, that'll be interesting. I'll let you guys know.
cool. Yeah,
What happens.
I think I'm just gonna stay in the call for like another half hour and just like read the content commitment thing again, and then think. Yeah, while Vivek goes and does his thing.
Yeah, I have to leave because I have to charge like all of my devices right now.
Yeah.
Um,
Yeah, go for it.
But yeah, it was good. I think that's a really good next step. I feel like even this might be a bit too far from BLS, but I don't know what else there is. So,
Yeah, we might be able to get something even simpler. Like another thing I want to do is like, that I think is actually of like very practical use is like witness encryption to a valid signature, because then you can do really cool shit where it's like, I have a valid email from the Coinbase public key, and you can decrypt and encrypt stuff to that signature.
witness encryption to RSA.
To like a valid RSA signature. I think witness encryption to a specific RSA signature exists, but that's like not very interesting.
Like a valid RSA signature, but given certain public inputs is the problem, right? Like this Coinbase email thing is only compelling if you know the subject is X or something.
Well, even just starting with this, I think you could do some cool stuff. Like it's also like, maybe not Coinbase in particular, but
And you
it's
have to know
like,
the exact email. What do you mean?
wait, you mean you're not fixing the message? Like you can do it with arbitrary messages?
No.
yeah. Like for example, like you receive an email from like a secret society, and like that signature can just be used to decrypt all information from the society.
Oh, like you're saying if the email's constant, like if you already know the email body.
No. I'm saying like you don't know the email body.
Well, like any RSA signature would fly.
Valid RSA signature from a public key. It's very similar to the KZG thing in that it's like just valid polynomial opening. I think like this sort of generalized thing is like really interesting and useful for different use cases.
Any RSA signature seems too broad. Like you have to prove something about the message in the signature, no?
Well, if we can do the Groth16 thing, we can do that.
Or it's like the same as KZG, right? Or like kind of.
It's very similar. It's just like a general
Yeah.
thing. Like we're going for something like literally like 100 to maybe 1,000,000 times harder than valid RSA signature. Or like fine, valid Schnorr signature, because that's like nice and structured and elliptic curvy. Like that's fine too as like a starting point. Actually, but I don't know if you can verify a Schnorr signature without a message. Because yeah, some of this stuff, like for example, ECDSA, like you verify with both a public key and a message. You can't verify with just a public key, but if there's any schemes in which you can verify with just a public key.
Verify with just a public key?
Wait, can you even do this?
Wait, surely there's no way, right?
Can you even do this with BLS? Which is the simplest of all.
Wait, because if you just wait, what?
Yeah, this doesn't even work. Like you kind of need a message as well. Okay, fine. Then I guess the next level up is like message with some properties or something like this. Yeah, and then I guess maybe like the minimum thing on top of KZG is like I think actually the KCG witness encryption paper covers this, but like, can you encrypt to something to knowledge of like one of 5 different openings?
Oh, does it do that?
I think it's in there somewhere. Like it adds some. I mean, it's either like the trivial thing of like you just encrypt all of them, or like there's might be some more clever way to do it. I haven't like read that paper in detail, which I will also.
Isn't this like the batch or the threshold BLS version?
Maybe they seem different enough that wouldn't work.
It's like T out. You need T out event signatures to decrypt.
Yeah. I forget. I actually I know that's in the McFly paper too, but I never sat down and looked at that. Oh my god, there's so many fucking papers. It's a good feeling though. Okay. Oh right, yeah. SWE for BLS multi-signatures. Right. Oh wait, no, but this isn't threshold. This is just like you have n or something, right? Like, is this what you're talking about, Nathan? Like in the.
I think they define or they construct threshold in the paper.
Oh, in McFly.
Yeah, it's like section 5 or some shit.
Right. Yeah, that actually is the thing that they do. It's the threshold thing. Yeah. Yeah, I wonder if there's like some way to combine different tricks from all these things to get something that's like slightly more useful. Because the current KCG witness encryption thing, like I've been like lightly thinking about it in the back of my head, and like it feels like pretty fucking perfect for laconic OT, but like isn't expressive to do anything else. So even if we get a little bit of a bump in expressivity, we might be able to do some more like interesting things.
I remember like thinking a little bit of like abusing like linearity of like KCG commitments, because you could like add them and then like that means like you force like, or it's like if you have like a bunch of commitments from people, then you could add them all and like encrypt something with that, and then you're basically forcing them all to collude in order to decrypt it.
This is interesting. I like this.
And you can do like a secret sharing thing where like none of them learn anything about anyone else's commitment or anyone else's secret or something. But
Interesting.
All right, I'm head out. This was fun.
Sounds good.
I will see you folks later.
Yeah.
See you, Nathan. Thanks for calling.
Yeah.
This is really
Yeah, it was
good.
nice talking to you.
Yeah. Sorry, do you like have school and stuff?
Yeah, I'm kind of like chilling right now. I feel like it's not that busy, but
Okay.
Nice.
mainly 031. That shit is like
Oh my god.
not it.
Retarded class.
Yeah, I petitioned 172 for 031 and then just didn't do it.
Wait, really?
Yeah.
Wait. But I heard like it's a lot harder now.
Yeah,
Or
I
I
also
heard like a lot of
that.
people tried petitioning 031, but it didn't work.
So the thing is, I petitioned 172 and the fact that I did lead poker for 031. Like, I sent them my GitHub repo and I was like, look, we wrote a GitHub repo with like 50,000 lines of code. Like, we had all these fucking tests. Like, I learned how to do this stuff in 031. I think they were just like, okay.
Yeah, I mean, I haven't built a 50,000 line repo.
Yeah.
But I mean, yeah, it's like fine. I just take it.
Yeah, it's fine.
All right, see you then.
Yeah, see ya.
Alright, see you later.
As well. All right, nice talking. I'll let you guys know what I get.
Yeah, see you later.
Take care.
You too.